Hello everyone, thanks for having me. My name is Alex Lin, and the paper that I'm about to present, titled Rotational Self-Motion Cues Improve Spatial Learning When Teleporting in Virtual Environments. This was part of some of my dissertation work that I did at Iowa State University with my advisor John Kelly and my other collaborators Nathan Sepich, Lucia Sherip, Grace Freed, and Stephen Gilbert in the navigation lab. I would also like to acknowledge the National Science Foundation for supporting this work. So when discussing virtual reality head-mounted displays, one key feature is the ability for users to explore virtual environments by physically walking to translate, that is to change position, and physically turning to change one's orientation. And so using a novel concordance framework, walking in VR would be considered a concordant locomotion interface because movement in the virtual environment is in agreement with movement of the body, as you can see with these two examples here. And so these self-motion cues associated with movement of the body are vital for keeping track of one's self-location. And this is a spatial cognitive process called spatial updating, which is keeping track of your position and orientation over time during self-motion. However, real walking is not always feasible, especially for everyday VR consumers, because of the limited track physical space. As you can see, eventually users would just run out of room to walk. And so some alternative locomotion interfaces have been developed to mitigate this, to work around this issue. One locomotion interface that is sometimes seen in VR video games, whereby the user can smoothly move through the virtual environment by using a gamepad or a joystick without any self-motion cues. However, there's evidence that interfaces with smooth visual motion, where you receive visual inputs but limited self-motion cues associated with movement of the body, can often cause symptoms of motion sickness. And so therefore, VR designers and developers have come up with other locomotion interfaces to mitigate this. Namely teleporting. And so teleporting is a very popular user interface used in many VR video games that allow users to explore large virtual environments. One reason it's popular is because it's easy to use, and second, it mitigates these symptoms associated with motion sickness. And so to teleport, the user would point to a location in space using a controller, and then with the push of a button, the user is then teleported to that location without any accompanying self-motion cues. And so in this example, in a VR video game called VR Lab, the user, we call this a partially concordant teleporting interface because movement in the virtual environment through rotations of the body to change one's orientation is in agreement with movement of the body. But teleporting to translate is not in agreement with movement of the body, and therefore we call it partially concordant teleporting. In this other interface, this is called discordant teleporting, used in a VR video game called Robo Recall. Here, similar to the other teleporting interface, the user teleports to translate, to change position, but what they're also doing, if you notice, is also changing their orientation using the controller. So when they arrive at that location or that position, they're also oriented in that direction. So they're teleporting in that direction as well. And so this teleporting interface has essentially no self-motion cues associated with translations or rotations. And so there are several use cases in which a teleporting interface like this would be used. One where users may want to experience VR in a seated position, or they're seated on a couch, for instance. For other populations who might be mobilely impaired, this would be an interface that would be commonly used. Or for some use cases in which a user is seated on an airplane, unable to move their body. And so that said, there has been some past work that has demonstrated spatial cognitive costs associated with teleporting interfaces that I just described, especially during small-scale movement when performing triangle completion tasks. As more self-motion cues are removed, there's more disorientation as a result. However, there's not much data about the effects of teleporting when trying to learn a large-scale virtual environment. And so many VR video games actually enable users to explore these large virtual environments, but there's very little data in understanding what its effects are when exploring these virtual environments. And so based on past research, we expect that rotational self-motion cues when teleporting would contribute to more accurate representations than a teleporting interface like discordant teleporting, where there are no self-motion cues. And so the goal of this study was to evaluate the effect of rotational self-motion cues when using a partially concordant and discordant teleporting interface on surveyed knowledge acquisition for large-scale virtual environments. If you're interested in learning more, aside from the paper, there's pre-registration and data publicly available on the Open Science Framework. And that link is available on the paper. So moving on to the methods, 118 participants were recruited from an undergraduate psychology subject pool from Iowa State University. Gender was approximately balanced across the two conditions. And of 118 participants, 107 remained in the final analysis. And more details are outlined in the paper for removal of those participants. So in a between participant design, participants were assigned to either the partially concordant teleporting interface or the discordant teleporting interface. And after some training with the assigned interface, they were instructed to learn a large-scale virtual environment by locating 6 different objects scattered throughout that environment. So here's a demonstration of the partially concordant teleporting interface that was used in this experiment. So you can see the users changing, teleporting to change their position, but they're turning their body, right, to rotate. And so here you can see on the controller the list of the 6 objects, or here is just 5, but there are six objects located on the controller that they can see at all times to keep track of which objects they found. So here's an example of discordant teleporting, whereby the user is teleporting to change their position, but also teleporting to change their orientation. So I'll skip ahead here. And so you notice the user is just looking around, but their feet have to stay fixed in one location as they move around the virtual environment. So after learning, so this is a bird's eye view of the virtual environment that the participants were instructed to learn. And here are the different locations of the 6 objects scattered throughout the virtual environment. And so they were given 7 minutes to find all 6 objects. If they found the objects before the time expired, they were encouraged to continue exploring. If they were unable to find all the objects within the 7 minutes, the experimenter then guided them to each of the remaining objects. And so to assess fidelity of survey knowledge, we use two measures. One called the scene-dependent, orientation-dependent perceptual pointing task. It's a mouthful, which we'll refer to as the SOP pointing task. And for this task, the participant stands at an object in the virtual environment and is asked to point to another unseen object. And so this was completed for every pair of objects, totaling 30 trials. And performance on this task was measured using absolute angular error. After completing the SOP task, participants were then asked to sketch a bird's eye view map of the virtual environment they experience from memory and indicate where each of those objects were located on their map, on their sketch map. Participants were provided the list of objects during this task, but they were not provided this bird's eye view. And so performance on this task was measured using a bidimensional regression, which allows the drawing to vary freely in scale and in orientation. So here's a demonstration of the SOP pointing task, where the user, it says, "You are now standing at the robots, please point the laser at the flower." And so here the user has to orient themselves and then point to where they think the flower is located, in the direction that the flower is located. And then the next trial starts. So now I'm going to present the results. So I want to draw your attention to the figure on the right. So on the y-axis, we have absolute angular error, pointing error average across all pairs of objects. 90 degrees is considered chance performance on this task. And the two colored bars represent the two different teleporting interfaces. And as predicted, we found a significant effect in that rotational self-motion cues when using the partially concordant teleporting would lead to greater accuracy in survey knowledge acquisition compared to discordant teleporting interface. And computing in Cohen's d, we also found a medium effect size. When looking at data for the sketch maps, this is the figure on the left is a wireframe of the target map. And so when comparing the participant sketch maps, we're always comparing the sketch maps to this target map. The bidimensional regression produces an R-squared value, which reflects the correlation between object locations drawn by the participant and object locations on the true map. And so other map features beyond the object locations, such as corridors, were not included in the analysis. And so here's an example of a highly accurate sketch map and an example of an inaccurate sketch map. And so when we look at the results across all participants between two interfaces, we also see, consistent with the SOP pointing task, we found a reliable effect of interface, demonstrating that sketch maps were more accurate with partially concordant teleporting than discordant teleporting interface, with also a medium effect size. So in conclusion, evidence from this study is consistent with past work on the contributions of self-motion cues, and the work we've done on teleporting and spatial updating, which suggests that there are spatial cognitive costs associated with using a discordant teleporting interface because access to these self-motion cues are removed. This work also supports theories that inputs from spatial updating contributes to survey knowledge acquisition. And because teleporting is a popular locomotion interface for many VR applications, VR designers should consider using a partially concordant teleporting interface where possible. And lastly, for future work, because this experiment only examined one large-scale virtual environment, future work should consider looking into whether survey knowledge acquisition varies when teleporting to navigate complex virtual environments. In addition, more work should also be done to understand ways to improve survey knowledge acquisition by leveraging work that's been done on environmental cues such as landmarks and boundaries or geometrical cues when exploring a virtual environment. And so that concludes my presentation. Here are my acknowledgements, and thank you.